Hi, in this video we will learn another method to solve system of linear equations called Gauss-Jordan elimination. This method is an elaborate version of Gaussian elimination in which instead of reducing augmented matrix to row echelon form, we reduce it to reduced row echelon form. So the steps for Gauss-Jordan elimination is exactly same as Gaussian elimination. So elimination. So let me just, for review, let me write it here. Step 1. So we have SLE, the system of linear equation or linear system. We write the augmented matrix of that. That's the first step. Step 2. Reduce the augmented matrix to reduced row echelon form. Well, you know there are differences between reduced echelon form and row echelon form. I will mention in a minute what are the differences. And step 3 is, well, it's time go back to SLE. So write the system of linear equations corresponding to reduced row echelon form that we have there, and solve it using back substitution. In this case, since we are going to do reduced row echelon form, the back substitution won't take that much work. Basically, some of these back substitution already done in row reduced, reducing augmented matrix to reduced row echelon form. Okay, so these are the steps as before. The only difference is here, reduced row echelon form. Now let us see what are the differences between, just quickly review, REF versus REF. Okay, so first thing is that the leading entries are 1. So in the REF, it could be any number, just leading non-zero entry. Here it needs to be 1. So it is called leading. Instead of calling leading entry, we call them leading 1. That's the first thing. The second difference is that not only the entries below the leading ones are 0, also the entries above the leading one are 0. In other words, all in a column with leading 1, in a column with a leading 1, every other entry is 0. Not only below, but above is also 0. So these two differences shows us that, well, when you reduce a matrix to row echelon form, you need to do few more steps to turn it to reduced row echelon form. First, do an operation like multiplying a scalar to a row to turn the leading entry to 1. Basically, you multiply the row by inverse of its leading entry. And for the second one, well, you already made everything below the row 0. Also use the same operation, row operation, something these ones. And make the entries above the leading ones also 0. Okay. We will do examples and you will see in the examples. As something else, again, before we move to examples, there is something about the row when you trying to solve a system using Gauss-Jordan elimination method, you can figure out the different cases of solutions when you row reduce the augmented matrix. So let me just write down what cases can come up. You row reduce and then you look for different possibilities. One thing is that the system has no solution. It's called inconsistent. What happens is that there is a row in these cases which is 0 on the left hand side of the separating line and non-zero on the right hand side. In this case, if you write down the SLE, or equation for this, you get 0 equal to non-zero. Yes, this means that it is not consistent. There is something wrong with this system, and well, it means that no solution exists for this one. Well, if there is a solution, either one or infinitely many, we call it consistent. And to check if something is consistent or not, you just need to check if there is any row which is of this form or not. If all the 0 rows have also 0 entry on the right hand side, then it is consistent. Now, the consistent case also has two different cases. One is that every column of the coefficient side. We are not talking about the constant, not the right hand side of the separating line, this left hand side. So if this is matrix, just something like this, just talking about these columns. Every column has a leading one of some of these rows. Okay, in that case, the system has unique solution. Exactly one solution. That's the other way of saying exactly one solution. And if it is not the case, so it means that it is consistent, but there are columns without leading one. There are, or is column without leading one. In that case, we will have infinitely many solutions. And actually, you know that the parameters are important in those cases. The number of parameters is exactly equal to number of leading ones. And yeah, you know, for each of these columns, you assign one of these parameters and try to solve the system. Okay, so after putting down all these things, now it's time to do some examples. I will complete the examples that we have done before. So solve the system, linear system given, solve the given linear system using Gauss-Jordan elimination. So first example, this example we actually did this one, x plus y plus 3z equals to 1, 2x plus y plus 4z is equal to 2, and x plus 2y plus 3z is equal to 4. Okay, let's start working on this. So we go first step to augmented matrix. 1 1 3 1, 2 1 4 2, and 1 2 3 4. Then you row reduce this guy. Well, we already actually did reduction of this to row echelon form. So reduce it. So what we did find was this matrix 1 2 3 0 1 0 1 3 and 0 0 negative 2 3. This is row echelon form, but we have to do a little bit more and turn it to reduced row echelon form. Reduced row echelon form, so the leading entries must be 1. This guy is good. This guy is good. This guy needs to be 1. So to do that one, let me erase this. To do that one, to turn it to 1, we can multiply the whole row 3 by the inverse of that leading entry. So it will be so this will be 1, this will be this guy. Yeah. Now, we have to check everything above the leading one. So now we have 3 leading ones. So this wasn't 1, so we turned it to 1. Okay. Here, now we have to make this guy, this is 1. Everything below is 0. That's all right. Now above, we have to make it 0. To make that one 0, we can use the operation that we are replacing row 1 by row 1 added to negative of that entry. So negative 2 multiplied to the row with the leading one. So this will be 0 1 0 1 3. Oh, not we need to wait for that. Negative 3 over 2, and then, well, we are not touching these rows, so this will be this. Okay. Now we want to make this operation. So 1 minus 2 times 0, 1. 2 times negative 2 times 1 is 0. 3 times negative 2 times 0 is 3. 1 times negative 2 times 3. 1 minus 2 times 3 is negative 5. Nice. So this is done. This is now very good. We have to check the entries above the last leading one here. This is already 1. We have to make that one 0. For that, we replace our 1 by our 1 minus 3 times R3. So R2 and R3 stay the same. For this part, 1 minus 3 times 0 is 1. 0 minus 3 times 0 is 0. 3 minus 3 times 1 is 0. Negative 5 minus 3 times 3 over 2. So that will give me 9 over 2 added to negative 5. Negative 5 plus 9 over 2. But that is nothing but negative half. Now the reduced row echelon form of this matrix is this guy. We are ready to go from here. This is the last step. We write down the equations for this guy. So this is x equal to negative half, y is equal to 3, and z is equal to negative 3 over 2. So that is the solution, the unique solution. You see, every column here, every column has a leading one of the rows. This guy has this one, and this one. That means we have unique solution, and that's the unique solution we have here. Okay? Let's do another example. Example 2. This is the equation. X minus 3y plus 4z minus 6w is equal to 1 minus x plus 3y plus 2z equals to 0. So row augmented matrix of this is 1, negative 3, 4, negative 6. Oops, negative 6 is okay. And 1, negative 1, 3, 2, 0, 0. Then we did reduce this matrix to augmented to row echelon form, and what we got was this. Now, we have to go further and make it reduced row echelon form. Yes, so we have to make sure that leading entries are 1. This guy is leading entry. This guy is leading entry of row 2. This is already 1. This is not. We have to make it 1 by multiplying the whole row by the inverse of the leading entry of that row. So this will give us 4, negative 6, 1, 0, 0. And this will be 1. This will be negative 1. This will be 1 over 6. Okay? Now, this leading one, everything else in the column of this leading one is 0. Yeah? This leading one, oh, there is an entry in the column of that leading one which is not 0. So we have to make it, turn it to 0 by multiplying, so replacing row 1 by row 1 minus the entry we want to make 0 times to the entry with the leading one. So, okay. So subtract, this is 1, this is negative 3. 4 minus 4 times 1 is 0. Negative 4 times negative 1 is just 4. Add to negative 6, you get negative 2. Negative 2 times 1 over 6 is negative 2/3. 1 added to that. And this guy gives us 1 over 3. Okay. Now this is reduced row echelon form. And now we can determine if it is consistent or not. We don't have any row 0 on the left, non-zero on the right. So it is consistent. We have 2 rows, 2 columns which have leading 1. So there are 2 columns without leading 1. So we have infinitely many solutions. How many parameters we have? A number of parameters is the number of columns without leading 1. So I will choose S for this one, T for this one. And now write down the SLE here. So it will be X minus 3y minus 2z is equal to 1/3. 2w, sorry. There's a 4th entry. And this other guy is z minus w is equal to 1 over 6. And we decided to set y to be s and w to be t. Now, write back everything in order. X is going to be 1/3. Take this guy to the other side plus 3 times. Instead of t, we can use s. Plus, I'm taking this guy to the other side. Instead of w, you use t. Y, x, y is s. Z is 1/6 minus, plus w. W is t. And w itself is t. Now we have the equation, the solution. Yes, so the solution is going to be 1/3, 0, 1, 6. Let me just write the vector form of this. S coefficients are 3, 1. Z has no S in it, and W has no S. And T coefficients 1 are 2, 0, 1, 1. These are the solutions. You see that there are infinitely many. So for different values of T, you just turn them. T and S, you get different values. Okay. So these were examples. Again, row reduced echelon form is what we do reduce our augmented matrix to when you're doing the Gauss-Jordan elimination method. And the other things are pretty much the same thing, and you can use this method also to solve the given linear systems.